Today I'll solve one numerical problem based on pumping power and pressure across the pump. So here is the problem statement. A pump is transferring a fluid with a specific gravity of 1.65 from a storage tank through a 10 cm diameter suction pipe. So here this is the storage tank and this is suction pipe, and diameter the suction pipe is 10 cm. The velocity of the fluid in the suction pipe is 1.2 meter per second. So velocity, that is 1.2 meter per second. The pump discharges the fluid through a 6 cm diameter pipe to an elevated tank. So this is elevated tank and diameter of the discharge pipe is 6 cm. Then the discharge point is 20 meter. So discharge point is 20 meter above the storage tank. So from here to here the distance is 20 meter above the storage tank. Frictional losses are estimated to be 4 meter. So HL is equal to 4 meter. If the pump operates at an efficiency 80%, eta is 80%. Efficiency. Calculate the pressure developed by the pump, the theoretical power required for the pump. So we have to calculate pressure developed by the pump and theoretical power for the pump. Now here is the given data. Specific gravity is given 1.65, diameter of the suction pipe 10 cm, that is 0.10 meter, diameter of the discharge pipe 6 cm, that is 0.06 meter, velocity in the suction pipe 1.2 meter per second, height difference 20 meter. So from here to here, that is ZB is nothing but ZB minus ZA, so that is 20 meter, and then frictional loss is 4 meter. Now using continuity equation, so we know that suction pipe velocity, fluid velocity, that is V1 1.2 meter per second, but we have to calculate the velocity of the discharge pipeline. So using continuity equation, A1 V1 is equal to A2 V2. So A1 is pi D1 square by 4, A2 is pi D2 square by 4. So D1 is 0.10 meter, D2 is 0.06 meter. So V1 is 1.2 meters. So cross sectional area for A1 is suction pipeline cross sectional area, that is pi by 4, 0.10 whole square. So that is 0.00785 meter square. A2 is discharge pipeline cross sectional area, that is pi by 4, 0.06 whole square, that is 0.002827 meter square. And calculate the V2. So V2 will be A1 V1 by A2. So A1 is 0.007854, V1 is 1.2, and A2 is 0.002827. So that is 3.33 meter per second. Now Bernoulli's equation correctly for a pump system between point A and B. So I am using applying Bernoulli's equation point A and point B. So point A and point B. So now Bernoulli's equation will be PA by half rho VA square plus rho G ZA plus rho G HP is equal to PB half rho VB square plus rho G ZB plus rho G HL. Now here PA and PB, the pressure at the point A and B, BA is 0 because here no velocity, velocity at the surface negligible. VB is 3.33 meter per second, and that is outlet velocity. Height difference ZA minus ZB, actually ZB minus ZA, so that is 20 meter. Head added by the pump converted to the pressure, so that is HP. And HL is the 4 meter frictional head loss converted to the pressure. Okay, so that is that 4 meter. Now so starting with Bernoulli's equation, so same that Bernoulli's equation. So here that neglected VA, so VA is 0, so this is 0, and PA PB both point exposed to atmospheric pressure, so this will be cancelled out, this will be cancelled out. Okay, so GHP, if we simplify the equation, GHP, so the rho will be cancelled out for both sides. Okay, so that GHP will be half VB square plus G ZB minus ZA plus GHL. So HP will be 1 by 2G VB square plus ZB minus ZA plus HL. Now we have all this data, we can plug and we will get the HP. So V2 is 3.33 meter per second, G is 9.81 meter per second, Z2 minus Zn, actually ZB minus ZA, so that is 20 meter, and HL is 4 meter. So if we plug that, so HP will be half 3.33 whole square, so that is 33 whole square by 9.81 plus 20 is ZB minus ZA plus 4, so that is 24.54 meter. So HP. Now adjust for the pump efficiency. So pump efficiency is 80%, so eta is 0.80. the actual head the pump must be generated is HP actual is HP by eta, so that is 24.57 by 0.80, so that is 25.37 meter. So pump that HP, that pumping head we got, that is 25.37 meter. Now if we want to calculate that pump pressure across the pump, so we have to apply Bernoulli's equation 0.1 and 0.2. so P1 is half rho B1 square plus rho G Z1 plus rho G HP actual, then P2 plus half rho B2 square plus rho G Z2. so P1 and P2 pressure at the point 1 and 2, V1 and V2 velocity at the point 1 and 2, height difference Z2 and is equal to Z1, so that is horizontal and we can neglect that, and HP head added by the pump converted to the pressure, and HL the no frictional head loss near the pump assume, so that is actually 0, so we are not considering here. So now if we reorganize, so P2 minus P1 will be, so P2 minus P1 will be rho G HP actual here from here, okay, rho, so this is cancel out, Z1 is equal to Z2, okay, so we have P2 minus P1 is equal to rho G HP actual plus half rho V2 square minus V1 square. So rho is 1.65 into 1000, so 1650 kg per meter cube. V1 is 1.2 meter per second, V2 is 3.33 meter per second. So now the pressure difference across the pump is given by, so we plug all this value, rho 1650, G 9.81, P actual, HP actual 25.37 plus half rho 1650, V2 3.33 whole square minus 1.2 whole square. Now after doing plugging values, and then if we calculate P2 minus P1, so that will be 418.611.85 Pascal, and that is 418.61 kilopascal. So thus the pressure difference across the pump is approximately 418.67 kilopascal. Now we have to calculate pumping power. So theoretical power required by the pump is given by that P power rho GQ HP actual by 1000. So now that is KW. So Q is here A1 V1, so that is 0.007854, okay, into 1.2, so that is 0.009425 meter cube per second. Now so here that power you calculate 1650 into 9.81 into 0.009425 into 25.37 by 1000, so we'll get pumping power is 3.87 kilowatt. So thus the theoretical power required is 3.754 in kiloW, that kW means kilowatt. Oh, that is 3.87, that is 3.87 kiloW. Okay, so that's it. Thank you.